Hi, my name is Xiaofeng. Today I'm going to talk about SwitchFlow, preemptive multitasking for deep learning. The success of deep learning can be attributed to the enormous amount of data available to the model training and the advent of fast GPUs. Recent advances in GPU accelerators make numerous groundbreaking killer applications. For example, AlphaGo can play the board game Go, and it won all three games against Keqi in May 2017. OpenAI devised a huge language model with 175 billion parameters called Generative Pre-trained Transformer 3 in 2020. Self-driving car is also evolving fast all over the world. Google's DeepMind designed AlphaFold that can perform predictions of protein structure. Nowadays, more sophisticated models can be trained at an unprecedented speed to invent more useful models to solve real-world hard problems. Deep learning framework plays an important role in helping researchers and practitioners to design, train, deploy deep learning models. Two mainstream deep learning frameworks are TensorFlow and PyTorch from Google and Facebook, respectively. These two frameworks support various accelerators, for example, GPUs and TPUs, and can scale elastically in distributed training. The initial development philosophy of these two frameworks are different in execution mode. Initially, TensorFlow prefers static graph mode, while PyTorch's default execution mode is dynamic graph mode, which will be explained in later slides. But now, both are performant for training and easy for deployment in both modes. Due to the fundamental infrastructure, deep learning frameworks make programming complex models not only easier, but also more efficient on various accelerators. They also fill the gap between research and production. The framework provides a runtime to train and serve the model. Deep learning processing is a complex pipeline, including data loading, pre-processing on CPUs, and execution on GPUs. The model is expressed as a computation graph. Nodes are called kernels or operators. Each operator or node in the computation graph may be implemented or optimized by a machine learning library, for example, cuDNN, cuBLAS. Edges represent data flow between nodes. Training involves forward propagation and backward propagation. Weights or model parameters are updated at each step with a forward and backward pass. Empirically, forward pass is 2 times faster than backward pass. Once the training is completed, the saved model is loaded into the inference runtime to deploy and serve users' requests. Various frameworks host and optimize inference models, such as TF-serving and TorchServe. We can see that it is challenging to reason about the whole stack performance and multiplex multiple deep learning models. Like in conventional workload co-location, deep learning multitasking should meet different service level objectives for heterogeneous workloads. Deep learning workloads can be broadly characterized into training and serving. Training workloads are throughput-oriented and computationally expensive long run. By contrast, serving workloads have a tight latency requirement but execute for the short term. If the system only hosts one service, it leads to low utilization in the production environment, since online inference requests often arrive unpredictably and stochastically. Therefore, the design goal is to improve the system utilization and also guarantee inference latency. Existing solutions consist of spatial and temporal multitasking. Spatial multitasking partitions resources among multiple tasks and executes them simultaneously if their combined size can fit in the device memory. Modern GPUs support concurrent execution of several small kernels to improve device utilization. Temporal multitasking assigns each task a time quantum during which the device is dedicated to one task at a time. Both mechanisms are proven effective for improving GPU utilization, but deep learning workloads on GPU pose different challenges. In order to improve GPU utilization, we co-run two resident training jobs on a V100 GPU at the same time by using spatial sharing of GPU. We used NV-proof to profile the V100 GPU, and the timeline shows kernel execution details. By zooming in the timeline, we observe kernels can currently execute on a single GPU. Unfortunately, there is no real performance benefit due to spatial sharing. The result is that execution time is prolonged significantly by almost 2 times due to contentions on shared GPU resources. We also observe serialization between a significant portion of kernels. In this case, kernels cannot benefit from execution at the same time at all. We found that the root cause is that low-level machine learning libraries aggressively optimize each operator to fully utilize GPU, not considering sharing. Time slicing allows deep learning models to take turns to execute at the end of each session, that is, after finishing a mini batch. Since time slicing GPUs among multiple deep learning workloads has been explored to provide better quality of service for inference jobs, we try to spot the problem by running a model either in training or in inference. During a time slice consisting of one or more sessions, GPU is dedicated to only one deep learning workload, that is, only the nodes from one computation graph are executed. On GPU, we use TensorFlow timeline to profile the kernel execution time and the session time, that is, mini batch step time. In the right figure, we profile training jobs of Resident 50, VGG16, Mobile V2. The kernel execution time ranges from 66% to 89% of the total session time. While still inference jobs of those three models have even lower utilization, the ratio of kernel time is from 10% to 60%. For more details of other models on different devices, please refer our paper. The result in the right figures indicate that jobs, especially inference jobs, in time slicing mode result in low GPU utilization when it runs in solo mode, because GPU kernels have time bubbles between each other and are not executing back-to-back. Besides, data loader is not efficient to feed data to the model. We propose SwitchFlow that allows users to provision GPU resources for their models without concerns about interference from other models or memory overcommitment. The key idea is that we break a computation graph into subgraphs. Each one is corresponding to computation on a different device, CPU or GPU. Scheduling subgraphs allows computation from different models to overlap. We add a session manager to handle all jobs from all users and implement the thread pool scheduler to do jobs preemption. In the following slides, we will discuss the solutions to the following challenges: how to preempt a deep learning model that have operators dispatched or interleaved with other models, how to effectively schedule subgraphs to overlap computation on different devices while avoiding contention on the same device. The result is a design that enables a low-latency, low-cost preemption mechanism to deschedule an entire computation graph without throughput loss and guaranteeing quality of service for both training jobs and inference jobs in a multi-tenant environment.